Hello and welcome back to the world's most exciting flip video series. Just wanted to delve into chapter 17 a little bit. We're going to start with just a little introduction to titrations and kind of go through just generally the idea of the reactions that are going to go on and some of the related concepts to that. And then in the coming days, we'll talk a little bit more about what that looks like from a graphical perspective. So we'll kind of look at titration curves. We'll then talk about what that means from a pH indicator perspective, so things that change color, like phenolphthalein that you may recall from the Chem 2 lab, and some other things like that. And then we'll kind of talk a little bit more about some of those related ideas, wrap up titrations over the next few days, and then we'll talk a little bit about the other aspect of Chapter 17, which is solubility product. More on that in the days to come. So before we kind of get into the specifics of the reactions, the first thing to kind of understand about titrations is that we're talking about this idea that you're trying to deduce something about a solution, a piece of information that you don't yet know by reacting with a known substance. So you're basically trying to say, I don't know the molarity of this thing, or I don't know the strength of this thing, or whatever. So what you're going to do is react an unknown with a known. And that's how titrations are generally used. The College Board, sort of in its infinite wisdom, sort of got away from this and went more to the what is the pH of these two things when you react them together. That's usually not how a titration works, because pH is pretty easy to figure out. What you really would want to be able to do is say, I don't know the molarity of this thing. What must the molarity be if I can produce a certain pH? But mathematically, they sort of got away from that as time went on. But that is generally what you use a titration for, is you don't know the molarity, you don't know the strength of an acid or a base, so you react it with a known one in order to learn about it. And that's a much more useful process than just saying, well, what's the pH if I mix these two things together? Theoretically, you should be able to find the pH of the things mixed together pretty easily. So a couple things that we should just generally think about. If we are talking about acid-base titrations, which we will be for now, the three main options that we'll have will be a strong acid and a strong base. And we won't spend much time on those because the College Board never did, even when they included this in the material, because there's no equilibrium there. There's also a weak acid plus strong base. That was probably their most preferred version of things. And then, of course, we could flip that and have the strong acid and weak base. So we'll talk about each of those in turn as we go through this. The strong and strong thing is generally not particularly exciting, simply because there is no equilibrium. So if you take a strong acid like HCl and react it with a strong base like KOH, well, from a net ionic perspective, we know that potassium never does anything, so we're looking at OH minus, and because potassium never does anything, neither does the chloride ion, so it's out. So all we're really looking at in a simplified net ionic way is the formation of water, which certainly is a significant event, but it's just not particularly interesting from an equilibrium perspective. There is no equilibrium, as you'll notice here. We've got the unidirectional arrow, one that we haven't written a whole lot lately, but that is sort of what's going on there. You just add the acid and the base and you make water. Of greater interest, far greater interest, honestly, is what's going to happen when we add one of the weak options, either acid or base, to one of the strong ones. So let's talk about that a little bit. So if we're talking about a weak acid plus a strong base, things get more interesting for a whole bunch of reasons. So let's say that we have an example of something like hydrofluoric acid and KOH. Again, from a net ionic perspective, I know that potassium never does anything, so it's out. But HF is in its main state right now. In other words, it is very, very, very much together. Maybe 5% of it has ionized. The other 95% are staying together as HF. So we're going to treat it as almost entirely HF. We're not really going to worry about the little bit of H plus and F minus that sort of are left here. So let's go ahead and think about HF plus OH minus. And it is slightly more complicated because theoretically, as I mentioned, the little bit of H plus and F minus that have been produced, the H plus that's been produced is actually what's going to react with the OH minus, but we'll imagine that's sort of happening in one step when technically it kind of happens in two. So what you would get at this point is the water that you would normally get from an acid-base reaction. So the H plus that HF is able to make with the OH minus that's there, they would react together to make water, and that would leave F minus floating around. Technically, it'll be floating around with the K plus, but because the K plus doesn't do anything, that's unimportant. That's sort of step one. This is the stoichiometry step, because what we're really concerned about here is the number of moles of things. So we'll talk more about that maybe in tomorrow's lesson, or maybe as an addendum to today's, depending on how the timing looks. So, if I had 3 moles of HF and 2 moles of OH minus, what's left over? And that's quite important, but maybe not one that we're going to talk too much about right now. But the key idea simply is, you can imagine if HF is in a greater amount than OH minus, if OH minus is the limiting reagent, OH minus is gone, and what I have left is some HF and some F minus, which means I have a mixture of conjugates, which then goes back to this common ion effect. I can plug them into the Ka expression or the Kb expression and find pH or molarity or whatever else that way. So that would be an easy path that we could take to kind of figure out some of this sort of thing, and depending on what the College Board wanted us to solve for. So there would be an equilibrium step that follows the stoichiometry step. So the equilibrium step that would follow would be plugging it all into the Ka equals H3O plus times F minus all over HF situation, where you take the amounts of HF and F minus that are left over and plug those in and either solve for Ka. So a good titration problem, honestly, is like, hey, when I do this, the pH is 4.4. What must Ka of this unknown acid be? And I'll probably link, there's a lot of videos out there about titrating vinegar, for instance, like what is the Ka of vinegar, what is the molarity of vinegar, something along those lines. And you can easily find that simply by measuring pH and sort of going from there. So, but that would be our next step. So there'd sort of be like a step 1 stoichiometry step and a step 2 equilibrium step. And that's why the AP kind of likes this, let alone the fact that it introduces a whole host of graphical considerations that we'll talk more about again in tomorrow's lesson. The next thing, of course, that we could talk about is what if we reversed the situation and had a strong acid and a weak base. And so in this case, let's say we've got HCl and NH3. Oops. Again, HCl is a strong acid, 100% ionizes. We don't really know a lot about solubility rules in this case, but again, the business end of the acid, the H plus, is what's important. The Cl minus will not be important. The ammonia will produce ammonium. As you do know, ammonium doesn't stick to anything in water, so chloride won't have anything to stick to once it kind of gets down to it. So the net ionic reaction is simply going to be the H plus NH3, and that's going to make NH4 plus. A better way to think about this is probably to think about it as H3O plus NH3 makes NH4 plus and water. So there's again that water as a product in an acid-base reaction that we're pretty much accustomed to. And again, this would be the stoichiometry step. Again, depending on the amounts that you have of your strong acid and strong base, of a weak base, you're going to get different results as a consequence. If there's more NH3 than there is H3O plus, you have leftover NH3, but you've also made NH4 plus along the way. So again, you're going to be left with conjugates. So during the titration, You're going to have equal amounts of those things at some point, or more of one or more of the other, and those are all things that the College Board is pretty much interested in. So again, this would be step one, the stoichiometry step. Step two, the equilibrium step, would then be to take KB and say, well, that could equal OH minus times NH4 plus all over NH3, and just plug in what you have. Now, there are some things that we'll kind of get into a little bit from a graphical perspective, but are still kind of important considerations to think about as we introduce the concept of titrations. Obviously, there's a surface view going on here, not really delving into the math of it, because again, the AP doesn't really want us to do the math of it. And in fact, the AP, even when it was going to include those, didn't want us to do the math of it. Now the AP apparently doesn't want us to know it at all. But some things to think about would be the different possibilities that you have here. There's sort of a possibility, option one, which isn't really a possibility, which is that you haven't added any strong acid or base to the weak titrant. And this is just, that's a chapter 16 x squared over molarity minus x kind of thing. So it really doesn't have anything to do with titrations, but it's something we'll certainly talk about. Step two then would be, well, what happens when there's more of the weak than the strong? That's when we're just going to use Ka or Kb. I'll talk about that. The most significant part of a titration, which is really the part that you are trying to get to, is the equivalence point. And at the equivalence point, then we've added equal moles of the weak and the strong. And curiously, at that point, that means that they've both been used up entirely. So all that remains is the conjugate of the weak, and that's really significant. That's really the thing that the College Board is really most interested in. It's kind of the thing I'm most interested in. We'll talk a lot about it when we get into the graphs a little bit tomorrow. That's of unbelievable importance in a lot of ways, because there's a lot of conceptual nuance there. There's also a lot of actual ramifications of what this means for a solution where the two things are in equal amounts, but there's still something left over that's quite important. It's not just going to be water that's left over. There might be the conjugate base, like F minus, or the conjugate acid, like NH4 plus, and that's going to have a huge impact. So we'll talk about that a little bit. What you would certainly use at this point would be the Kw over the Ka, or Kw over Kb, and then that would still equal the whole x squared over molarity minus x thing, but it's just a little more complicated than that, as we'll talk about in the coming days. And then lastly, although I don't know why you'd be worried about this, is if you added excess strong, that if you did the Chem 2 titration and you're supposed to get that light pink color, if you turned it fuchsia, you sort of know what it looks like when you've gone overboard. And so that overboard tendency when you get it fuchsia is of no use, because what you need is the equivalence point. That's the easiest point to sort of help you figure out the math. But again, they do occasionally, it's certainly worth thinking about 11. They do occasionally throw out problems about that, but it's really, this is more that you've overshot it. One thing that should be noted here in segment 2 that we sort of talked about, there is that idea of the half equivalence point, where we sort of talked a little bit the other day about optimal buffering capacity. You can actually create an optimal buffer. When you do this, it occurs at what's called the half equivalence point. That's when you've added exactly half as much of your strong acid or base as you have of your weak one. So you're literally halfway to the equivalence point. And when you've done that, you are now left with equal amounts of your weak acid and base. So you have equal amounts of HF and F minus, or NH3 and NH4 plus, etc. And when you have equal amounts of those, if you think back to the Ka or Kb expression, they will divide out. And when they divide out, that means that Ka equals H3O plus, or Kb equals OH minus. And that's a pretty interesting point, and there's a way to kind of figure out some things rather easily that way. And we'll talk about that a little bit. Again, the AP uses this concept, or used to use, of course. I keep thinking that it's 2019, silly me. That pKa is the same thing as pH at this point, or that pKb equals pOH, where simply p, the letter p, simply means negative log of whatever we're talking about. But I think that's probably enough for this little introduction today. Tomorrow we'll get into the curves and the graphs of all this stuff. We may tomorrow, or we may the day after, sort of thinking a little bit about what that looks like from a particle diagram perspective. What things are actually floating around in water at each of these points of a titration. What's floating around when there's just a weak acid or base? What's floating around when there's more weak acid than strong? What about at the equivalence point? What about beyond the equivalence point? So we may talk about all those things from a particle diagram perspective. But I think that's enough for now. Go out and enjoy the rest of your day. Think about AP Chem a little bit here and there, and try to keep on keeping on in this crazy world of ours. And we'll talk to you later. Bye.